I love that. Not everybody. Looks like class attendance is recovering a little bit now that the snow has started to go away, which is great. We are going to finish the conditional probability stuff today. We're going to do a couple of examples with Bayes' theorem so that you have a couple of examples to work with on your coming assignment. There aren't actually too many questions on Bayes' theorem that you can use, but there are a couple, so hopefully this will get you going. First one, multiple choice knowledge. This is kind of topical because a lot of people don't like multiple choice tests. A lot of people do. For those that don't believe in multiple choice tests, it's like not a good approximation of your knowledge, right? And then there's those that do. And you can sort of model it from one end of, say, the student end of things, that if you have, say, 60% knowledge, say your coverage is pretty good and the test coverage is pretty good, so given any random test question, you're going to get it 60% of the time. You might guess the rest and get a few points that way and get something like a C plus or a B minus, that kind of thing. From the instructor's point of view, there's a real question about what a question is telling you. Okay, so if the student answers a question correct, what's the chance that they actually know the answer? Okay, so we would like to believe that the test is actually doing what it's intended. That's what this question is about. Okay, so we're going to model it using probability. All right, so let's just say that with probability P, I said 60%, but maybe your knowledge is better, maybe your knowledge is worse. Okay, but with probability P, you know the answer to a question. All right, 1 minus P, you don't. And in the case that you don't, we model it as you have to guess. In reality, you probably don't have to guess. There may be some other factors that might allow you to eliminate an answer. But let's say that you get it down to a 1 in M chance at any moment. Okay, what's the conditional probability that a student knew an answer given that they answered the question correctly? Okay, notice that this is the opposite of what's given in the question. If the student knows the answer, they're going to answer it correctly. Okay, so that's definitely true. But if they answer it correctly, what's the chance that they actually knew the answer? Okay, all right, so this is ripe for using Bayes' theorem. Okay, so we're going to define two events as usual. I'm going to draw the probability tree this time so that you can see the two strands. I really want to connect the math with the diagrams today. Okay, so let's see B, the event student answers it correctly. And let K be the event the student knows the answer. Okay, so the way this problem is modeled, okay, if we were to draw a probability tree, the first thing that happens is, given a random question, the student either knows it or they don't. Okay, so I'm going to say, we'll put no over here, that's K, and we'll say doesn't know over here. That's K bar. Okay, and the probability that they know is given in the question, that's P. Probability they don't know is 1 minus P. Okay, so the next thing that happens is they answer the question. Okay, and they either get it correct or they don't. Okay, so question for you, what should I draw off of this node here, the left-hand node in the diagram? How should I complete the tree? Correct or incorrect? Okay, so one branch is correct, the other is incorrect. I'll put C and C bar. And what probability for each? Yeah, 1 over M, and 1 minus 1 over M. M minus 1 over M. Good. Let's look at the second bit of this, the right-hand node, right subtree. Okay, so if they know, what happens next when they answer the question? What should I add to the tree for this one? Say it again. It's the correct answer. So what should I draw in the tree? Good. Yeah. So there's only one branch. It's not a branch actually. Okay. So it's with probability 1 that they get the answer correct. Okay. What's the thing that we want? We want to know the probability that the student knows the answer given that they answered the question correctly. Okay. Notice that we're given the opposite of this, right? We're given in the problem the probability that the student answers correctly given that they know the answer. If they know the answer, the probability is 1. It's over here. It's actually, if they don't know it, we also know the probability. Okay, but because these things are flipped, that seems ripe for using Bayes' theorem, right? And just to show you this slide from last time. Okay, so there's a relationship between the probability of B given A versus probability of A given B. Okay, so you can say it's the ratio of those two. Exploded using the law of total probability, you notice there's some common things in the numerator and the denominator. There are two cases, basically, two strands. It either, B happens or B doesn't happen. And we're interested in the fraction of the time that B happens. Okay, so this is indeed what's happening in this diagram. That the bit that we're interested in is what happens when they answer correctly and they know. All right. Okay, so we're interested in that piece, but we have to factor in the fact that they might not know when they just guess correctly. Yeah. Okay, so actually, let's just copy that while we're here. Okay, so this is, we'll use this version here, so it's the probability of C given K times the probability of K. And we repeat that bit in the denominator. But there's also the case that they don't know. Okay, so that's got to be, and they guessed correctly. That's a K bar. It's not really well written there, pardon me. Okay. And we can just pluck these things off the diagram, right? Okay, so the probability that C given K is that 1, the probability of K that they know is P. Okay, so that's 1 times P. The denominator has the same thing, 1 times P. Okay, so that, just to make it clear what's happening, like, you know, if we were to do the conditional probability bit, right, the answer, the chances that they get it correct are these two strands. We just did this strand here, 1 times P, or P times 1. The other strand is this. Okay, so probability of that they got it correct, given that they didn't know, is 1 over m. And the probability that they didn't know is 1 minus P. Okay, so if you wanted to do it using the tree, you can still do it. But you're going to find it a little bit more efficient to just do it without the tree in a lot of cases, because, you know, you can sort of pick out what each of these things are from the these things. Anyway, back to the math. There's a lot of fractions in there. Best is to multiply through top and bottom by m to get rid of that 1 over m. So that will give us mp on the top. On the denominator, this will give us an mp on the bottom, and there will be a 1 minus p. Okay, so just to collect the m's together, that will give us, I guess that's plus p minus 1. Oh, wait a sec. No, sorry. Common factor is p. Pardon me. Yeah, so there's a, sorry. Common factor is p. That's m minus 1. That's better. Sorry, flopped in my head. Okay, cool. In terms of p's and m's, this is the generalization. Now, what does it all mean? Well, let's try it out. Okay, so I suggested P being 3/5. So let's say you're a 60% knowledge student. Okay, so you're expecting to pass the exam, and there's 5 questions per multiple choice question. This will get, let's see, so this would be 5 times 3/5, that's 3 on the top. Well, let's just do it. Let's see. It's 5 divided by 1 plus 3/5 times 4. Okay, so that's equal to 3 on the top, and the denominator here is, let's see, that's 12/5 plus another 5/5, so that's 17/5, and then we just invert that and we get 15/17. Okay, so the chances that they knew the answer, given that they answered the question correctly, is pretty good. 15/17, let's see, the 17th is roughly 6%, so this would be something around 87, 88%. It's pretty good, right? You feel pretty confident that the student actually knew the answer if they got it right. Okay, and you can try different cases here. The answers are pretty good as long as, you know, the probability is that they're on track to pass the test. So even if you have smaller choices to go from, the numbers are pretty strong. Okay, questions about this one? Yeah? Feel pretty good? All right, one more case for Bayes' theorem. And I want to use a different law of total probability than this one where there are multiple cases, not just B and B bar. Okay. So to get the third, or, you know, more cases in there, we're doing 3 cases. We're going to do the missing plane problem. Okay, so what's the missing plane problem? Plane's gone down on an island somewhere in one of 3 regions. 1, 2, or 3. It's in one of those regions. And region 1 is going to get searched. Okay, it's possible that you search the region and you fail to find the plane, and this is pretty realistic given that there's terrain considerations in that region. Okay, so there's a probability beta 1 that you will miss the plane in the region. Okay, if it went down there. Okay, so this is known as an overlook probability, and the question asks, what is the probability that the plane is actually in the ith region if you look in region 1 and you don't find the plane? Okay, so let's do our usual thing, okay, and write out some events to get started here. First of all, let Ri be the event that the plane went down in region I. Sorry, be the event. Okay, so that's the first thing that happens in this experiment, right? It's either R1, R2, or R3, and it's all equally likely, yeah? So this is 1/3, 1/3, 1/3. Okay, the next thing that happens is that they search region 1. And it's not found. Okay, so to continue with this diagram, if the plane is actually in region 1, that's a shame that we missed it. Okay, but it could be that you found it or you didn't find it. Okay, so it is not found in region 1. Okay, but it is. So the probability the plane will be found upon the search of the ith region when the region isn't. Okay, so this is 1 minus beta 1, I guess beta 1, not beta I. And with probability beta 1, you miss it. Okay, so you search region 1. What should I put in this part of the tree over here? If the plane is in region 2. So what was the question? What should I put in this tree? What should I put under this R2? What should I put there? It's either found or it's not found. Okay. It's either found in region 1 or it's not found in region 1. Okay, so if it's in region 2, I'm just going to build on what you said because I think there's a little bit of confusion and I think maybe there's a lot of people confused. Okay, so there's a plane. It fell down in one of these 3 regions. We don't know which. It's somewhere though. Okay. If it's in region 2 and we look in region 1, what's going on? Are we going to find it in region 1 or not? Right, if we're looking in region 1, are we going to find the plane there? No, what do you mean? You're going to find the plane in region 1? The plane is in region 2. Okay, so R1 and R2 and R3 is the event the plane is in region 1, 2, or 3. Okay, so if it's in region 2, it can't be in region 1, right? Right, okay. So the chances are that A be the event the plane is not found in region 1. It's 100% it's not going to be in region 1, right? So A occurs with 100%. And likewise, region 3, it is not there 100%. Okay, so it'd be nice to have these 2 things, but we'll find that, we just don't draw things that can't occur, right? We don't draw arms that have 0 probability, yeah? Okay. The probability that it lands in any region is equal at 1/3. And the search is unsuccessful. Okay, so more or less, we're conditioning on A. Okay, so all the cases, there's 1, there's another, there's a 3rd. Okay, so all the cases where the plane is not found are listed there. Okay, so the probability that it's in, that you didn't find the plane if it's in region 1 is beta 1. And the probability that you don't find the plane if it's in region 2 is 1. And the probability that, same thing for region 3. Okay, so your goal is to find the opposite of these. That it's in region 1 given that you searched unsuccessfully, that it's in region 2 given that you searched unsuccessfully, and region 3. It's probably worth showing the total probability thing again. Okay, so Bayes' theorem on the denominator has the law of total probability for, this is for 3 sets, okay, or case sets. We're going to use it for 3. Okay, so we're going to take it for all the 3 different cases, add them all up, and that's going to be the denominator in this this application of Bayes' theorem. Okay, so let's do that. All right, so we use Bayes' theorem. Okay, and we're just going to do all 3 of them at the same time. Okay, so the probability of Ri given A equals the probability of A given Ri times the probability of Ri. Okay, so that's the piece that we're interested in. And the denominator is the sum of all three of these. So A given R1 times the probability of R1. Okay, so we take all three cases in this total probability. And I'll give you a moment to catch up. Now, one nice thing that is part of this problem is that the probability of R1, R2, and R3 are all the same. And, we could basically do this if we wanted to. They just cancel. I'm going to write them out, though, just so that you see where they come from, because you can't always do that, all right? But anyway, those are going to cancel out, and I will stroke them out on the next step, all right? Okay, probability of A given Ri is different for all of them. I'm going to leave that alone, and we'll substitute that later for three different cases. And that's a third there. The other ones on the denominator are, okay, let's sum them in, beta 1 times a third, plus 1 times a third, plus 1 times a third. So you're hearing this beeping noise. I don't know if anyone else is hearing it. But... All right. Okay, so we just subbed in all these things, and these thirds are going to go away. The thing that we're left with is probability of A given Ri divided by, and we got a beta 1, and we got a 1 and a 1. We'll just combine those together to get 2. Okay, so the reason I did this is so that we wouldn't have to write out Bayes' theorem 3 times and do the consolidation. All I have to do is sub in I equals 1, 2, and 3. Okay, so let's do that now. And I'll just switch colors briefly so that it's clear that we're doing something else with this. Okay, so we sort of finish this thought. The probability of R1 given A. Okay, so this is the probability of A given R1, which is beta 1. So it's beta 1 over beta 1 plus 2. The probability of R2 given A is the probability of A given R2, and that's 1. So that's 1 divided by beta 1 plus 2. And the probability of R3 given A is going to be the probability of A given R3, which is 1 divided by beta 1 plus 2. Okay, so those last two things are the same. Okay, so what does it all mean? Well, let's try some numbers, okay, just to give us a sense of what's happening, all right? Let's try beta 1 is 0.3. Okay, so that means that with 30% probability, if the plane is in region 1, you're going to miss it, okay? You're going to fail to find it. Okay, so that means that the probability of R1 given A, okay, is 0.3 divided by 2.3, which is 13%. And the probability of R2 given A and the probability of R3 given A are the same. They're around 43.5%. So does it make sense? Well, yeah, if you search the region and it's, maybe you missed it, but your probability that it's there goes down because, you might have found it. 70% of the time you might have found it. And the likelihood of it being in the other regions goes up because, we looked and, maybe we missed it, but chances are it's in the other regions. That sort of makes sense, right? And in the degenerate cases, like say, beta 1 is 0, right? You never miss it if you look in there. So let's try beta 1 is 0 in this thing. The probability that it's in region 1 given that you didn't find it is 0 over 0 plus 2. It's 0, right? That makes sense. And the chances are a half. It's either 50-50 for the other two regions. That makes sense. And what if the overlook probability is 1? What if you're really stinking bad at searching? Okay, like it doesn't mean anything if you don't find it. Well, then try beta 1 is equal to 1. Well, that's 1 over 1 plus 2. You get 1/3 back. Okay, no extra information. 1 over 1/3. You're back to where you started. Okay, it actually makes a lot of sense in the degenerate cases, right? But your chances do improve a little bit with the extra information. Yeah? Kind of cool, right? Okay, questions about this one? Do you have to break down the cases to get the... Well, I mean, these two cases are the same. R2 and R3 are the same. But R1 is necessarily asymmetric from that, right? So I did it this way for efficiency. You could write out 3 different Bayes theorems and just do the 3 things. But, I wanted to save some writing. Nothing stopping you from doing it. Okay, other questions? Okay, it's time for a summary slide. All right. So this is it. Okay, so it's a great theorem in all of its entirety, and there are 3 different versions of the theorem. okay, depending on which law of total probability you sub in. All right, so let's just go over the law of total probability for just a second. The law of total probability says that you can try one case or another case, or maybe one of k different cases, as long as they partition the sample space and multiply their, use the multiplicative rule. You use this is, chances that it's a given b times, weighted by the probability of b. Okay, just to remind you, the multiplicative rule is working here. This is the probability of A intersect B and the probability of A intersect B bar. And those two pieces, if you were to draw a Venn diagram, would union, they're disjoint, and they would union to give you A. Okay, that's the k-set version, and each of these will substitute into these two versions of Bayes' theorem. This will be the most common one that you'll face, that there are exactly two cases, either it is or it isn't. They either tested positive for cancer or they didn't. Okay, so, or what was the one we did just now? They either got the question, so they either knew it or they didn't. Okay, so that was the multiple choice knowledge. Here in the missing plane example, there were 3 different cases. Okay, so you just take one out of that. Either way, it represents a fraction of the entire whole, what the condition space is. Okay, sometimes you have this nice situation where you just take the fraction of the probability. So that's the sort of the vanilla version. You're probably going to use this one the most often. Okay. Anyway, sorry, I'm supposed to highlight this fraction thing because this is actually what's going on in the diagram. Okay, so that piece is that blue piece there, or the piece that you're interested in is, well, I don't have BI everywhere, but we'll just say that's B1. Okay, so whichever piece you're interested in, that is the fraction of the whole. I'm going to show you a computing application of Bayes' theorem. It's not the most recent one, but it's still used today in your emailers, and it's spam filtering. Okay, Bayesian spam filters. Okay, this is a naive approach necessarily because the math gets tougher the more things we put in, but we can handle it with just this version of Bayes' theorem right here. Okay, so just to go over what the problem is, spam is, well, it's very tasty. Spiced ham is what it's supposed to stand for. I love that. Not everybody loves it, but whatever. But in the in sort of the electronic world, this represents something else. Okay, an annoyance where somebody is basically like hammering a button, okay, spamming the button, or in the case of bots, hammering the send button on email. Okay, so spam versus ham, ham being a phrase for legitimate email, tends to outnumber ham by 4 to 1. Okay, so the a priori on spam, if you just take a message and you don't do anything to it, it's around 80%. Okay, so our goal is to devise an algorithm to decide what is spam and what is not. The objective is to minimize false negatives, spam that is incorrectly allowed into the inbox, that is annoying. Also to minimize false positives, where you do the opposite. You tag ham as spam and it gets moved to junk. My estimate is that one of these two false positives or negatives is more annoying to you than the other. Is one more annoying to you than the other? Probably. Let's just quickly vote on which one you would find more annoying, a false negative or a false positive. Prepare to vote. You ready? Okay, let's vote. Who would find a false negative more annoying? Who would find a false positive more annoying? Yeah, me too. Okay, so a few of you found a false negative more annoying. I find them both annoying, but it tends to generate more problems in my life when I, something gets tagged and sent to junk that I actually need it. Okay. Okay. So anyway, we're going to use Bayes' theorem to build a spam filter. All right. How does it work? Well, you train a data set, and the nice thing about this sort of approach is that you can use a data set that's tailored to each one of you. Okay, so you can each have your own set of keywords that you might find offensive, and they're not universal. Okay, so some people like to have, I don't know, some people have friends, okay, or professor names that are sort of unusual, and they might be associated with unsolicited mail. Okay, they might sound like a funny word, and you might want that mail, and you can train the network based on that. Some people have relatives in Nigeria, right? The Nigerian prince letter, whatever. Some people actually need to communicate with people in Nigeria. Okay, so you can train it for your own purposes. That's really great. But there are some words that I'll just suggest are probably not what you want. Maybe they are, but probably not. Okay, so fortune, Viagra, stock. We'll see a couple of things in the example. Herbal and enhancement are going to be the words we're after. But anyway, we're counting the frequency counts of words like that appear in spam versus when they appear in ham. Okay, and often they appear more frequently in spam than ham. And when you tag them as legitimate or illegitimate, your frequency counter goes up for all the words in that email. Okay, we're going to do a Bayes theorem on this and sort of see what the tolerance is like. Just to note here that, you know, what would be sort of a tolerance that we would be willing, you know, to live with in this false positive thing. Maybe a score of around 90% or more would be acceptable for tagging this thing, but maybe something higher, maybe something lower. Okay, so the threshold is something that you need to calibrate. These things are still in use. They're not the first line of defense because they're easy to fool. You can add a bunch of legitimate words onto an email or intentionally misspell things. You know, like Viagra, you can put at signs and, you know, use different diacritical things on the eyes and fool a spam filter. So there's it's part, you know, it's still used as part of a larger package, but it's not the primary defense. Okay, so the problem. Herbal appears 1 out of 1,200 training messages. Okay, legitimate messages, a lot less frequent, 50 out of 2,000. Okay, very infrequent. Okay, what's the probability that an incoming email that has the word herbal in it is spam? Now, we assume no prejudice about any incoming email, which may or may not be a good assumption. Given what I just told you, you know, it's like 80% likely it's going to be spam. So maybe the chances, you know, the a priori chances should be something higher. But this here will mean that the probability of spam is assumed to be 0.5. Okay, so define events. SP is incoming email spam. We got that at 0.5. W1 is the incoming email contains herbal. Okay, we have 1 out of 1,200 and 50 out of 2,000 as our conditional probabilities. The probability that W1 appears, okay, so herbal appears, given that it's spam, is 100 out of 1,200, which is 1/12. And the probability that it appears in ham is 50 out of 2,000, which is 1 in 40. Okay, so much, much less. Okay, we apply Bayes' theorem. Okay, so I've written out Bayes' theorem here. We're just going to do the substitution real quick. One nice thing about this thing being 0.5, again, these things cancel each other out, so that makes the calculation a little bit more friendly. If you had some, you know, a different starting probability, you'd have to put them in, okay, and weight them properly. Anyway, so this is going to be a 12th divided by a 12th plus a 40th, and if you run that through the calculator, it's around 77%, 0.77. And this is probably not enough for you to, you know, tag it as spam. Okay, it probably is not going to meet your threshold, which is usually around 90%. But if you assumed that the probability of spam was 0.8, then the probability of spam, given that W1 appears, is over 90%. Okay, and it would get tagged. So I don't know what's right here, but usually we assume no prejudice, which probably reduces false positives down a great deal. Okay, so maybe this one word is not enough. So you have a whole dictionary of words and you try and combine them together. Okay, and there are words that are good actually, like if, you know, somebody is emailing you, like your professor or something, you know, that those words might actually legitimize your, you know, it's a friend of yours, you know, a common name. That might legitimize an email. So there's some words that are positive. I'm sort of looking at negative words here. Okay, so what happens if you try to combine forces? Well, you end up with W2. So I've got enhancement as the second word, and we're looking at an email that has both herbal and enhancement. Okay, so the Bayes equation ends up being, it contains both these words, W1 and W2, and it's either spam or not spam. And this is a problem because we don't know the occurrences of both of these things. Okay, so the statistics database, it just keeps a frequency count. It doesn't look at, you know, overlaps. It doesn't overlap events. Okay, so what is done, and this is a simplifying assumption, an approximation, if you will, is you assume that W1 and W2 occur independently. And I'm going to spend a lot of time on independence in the next unit, but independent events allow us to do something mathematically to this, and it will be to break up the intersections and use multiplication instead. Okay, so this is an approximation. What are the chances that these two things are independent? Probably not good. Probably if somebody is saying herbal, there's a good chance they're saying enhancement in the same email, and vice versa. Okay, but anyway, the round-off error is small, as it turns out. So what do? We blow this up as a product of W1 given SP and and W2 given SP. Okay, so we multiply, so any intersect becomes multiply if they're independent. so that's what, I mean, I could have saved myself some writing a little bit because those, these things could have been wiped out. Anyway, sorry about that. Anyway, so we can just multiply the fractions out. Okay, so it ends up being a product of fractions. And we have the same 1/12 that we had before. I'm going to color code it just a little bit here. We're multiplying by 1/15 this time, so that's 8 over 1200 divided by 12th times a 15th. Okay, so the extra information is in red here, and it's 3 out of 200. Okay, and that extra information, those 2 bits, will give us a threshold, or a probability of span of 0.94, which is probably going to exceed the threshold. Yeah. Okay, so this is just a very quick application of Bayes' theorem. Any questions about this? Is it a good assumption that they're both independent? They're probably not like purely independent, but these numbers here probably match this. It's not too far off. So it is approximate, not exact. Yeah. Okay. We have our next unit available, and it's not a long unit. I expect this to be done by Friday, which is going to be good timing for the reading break. Okay. So we have a couple minutes. I just want to review where we've been and draw a highlight over a couple things. Okay. So here's the story so far. We've been talking about conditional probability, which is this extra information B added in, and it will change the value of the probability of A sometimes. Okay. Why? Because you're changing the sample space to B, and the formula ended up being this, or this if you cross multiply. Okay, so you get a multiplicative rule, and this applies very well to the probability trees that we've been working on. There are a couple other things that come from the previous unit that are going to be useful for our purposes in this unit. One is the monotonicity rule, that if A is a subset of B, then the condition probability will obey inequality. And the law of total probability, okay, again, the hypothesis either B happens or B complement happens, and you get A back. Now, something I mentioned just recently, too, because we were talking about independence, something I mentioned before was what happens if this thing is equal to the probability of A. Okay, so if that is equal to the probability of A, in other words, the probability of A given B gets you the probability of A back, it means that the extra information given by B actually didn't change anything. B didn't matter. It's not that the sample space didn't shrink, we didn't exclude any cases or whatever, but B and A seem to just not matter to each other at all. And this is essentially what independence means. Okay, so another way is to just sub this in for this. Okay, so either way you look at this, you cross multiply or just sub it in, you get the probability of A intersect B equals the probability of A times the probability of B. Okay, so that is indeed the definition of independence. Okay, so if the probability of A given B equals the probability of A, then A is independent of B. That's the definition I like. Other textbooks do something a little bit different. They just define 2 events are independent if this equation holds. And the reason I don't like this as much is that